Now see, next biasing technique is collector to emitter feedback bias. Now here the circuit shows the collector to emitter feedback bias circuit. Now see how to represent the currents. Now first here, this is a NPN transistor symbol, and this is a emitter terminal. This is base terminal. This is collector terminal. Now current through this collector is IC, current through base is IB, current through emitter is IE. Okay, these are your emitter base collector currents. Now here, current through this one is IC, this one is IB. Now if you observe this node, IB, IC both are away from the nodes. That means what is the current to RC and it must be entering into the node. That means IB plus IC. Now here, algebraic sum of the currents entering is equal to algebraic sum of the currents away from the node. So that's why it is RC. Current to RC is must be IB plus IC. Now IB plus IC is equal to IB plus IC. It is satisfied. Okay. Now again I'm going to write the input loop equation as well as output loop equation. Now first see the input loop equations here. VCC voltage rise, across resistor RC voltage drop, across resistor RB voltage drop, across this transistor voltage drop, across RE also voltage drop. This one, this one, this one, this one. All are voltage drops, whereas VCC is voltage rise. Now write the equation. Voltage rise is equal to voltage drops, and from that VCC is equal to, see here, RC into IB plus IC plus RB into IB plus VBE plus IA into RE. Now see here, I written here VCC is equal to RC into IB plus IC plus VCE plus IE RE. Again substitute this IA is equal to IB plus IC. IA is equal to IB plus IC. Okay. Now this is the equation related to input and again write the equation related to output and now here this is the related to output and VCC, RC, VCE, RE. These are related to output. Now here VCC voltage rise is equal to RC into IB plus IC plus VCE plus IE into RE. Okay. Now this is the output loop equation. Now if you observe in the circuit, here this RC and RE connected between input loop as well as output loop. Now here RC and RE both are connected between input loop as well as output loop. So that's why when you are writing the input, you are getting this RC as well as RE. And in the case of output loop also, you are getting this RC and RE. Whereas this RB is connected to only input loop. Okay. Now see here. This is your output loop equation. Now again substitute this IE is equal to IB plus IC. Okay. From this equation, write the equation in terms of IB and write the equation in terms of IB. Now IB is given by VCC minus VBE minus IC into RC plus RE by RC plus RB plus RE. From this equation you can write the IB as like this. Okay. Now determine the stability factor. Yes. Now for that again I am considering this above equation here. Okay. Now why we are taking this IB? Why? Because S is equal to 1 plus beta by 1 minus beta into dou IB by dou I. Okay. So in that case we require dou IB by dou IC. So that's why I am taking this equation. Now here. Now differentiate this IB with respect to IC and it becomes dou IB by dou IC is equal to VCC constant 0, VBE constant 0. That means differentiation of this is 0 only. Differentiation of VCC is 0, differentiation of VBE is 0. And after DIC by DIC, it will become 1. 1 into minus 1, minus 1. So that's why it is minus 1 into RC plus RE by RB plus RC plus RE. See here. This is the equation for dou IB by dou IC. Okay. Now substitute this dou IB by dou IC in the S factor. Already I explained that S factor in my previous class. S factor is given by here S factor is given by X is equal to 1 plus beta by 1 minus beta into dou IB by dou IC. Okay. This is the stability factor. Now substitute this dou IB by dou IC in this equation. Okay. Now it is 1 plus beta by 1. Here already we have minus. Here also minus. Minus and minus plus. Plus beta into dou IB by dou IC. That is RC plus RE by RB plus RC plus RC. Now this is the stability factor S in the case of collector feedback. Now see here whether the stability factor is decreased or not when compared to the remaining two biasing techniques. Now here. Now here 1 plus beta. That means when compared to this stability factor, this is decreased. Why? Because 1 plus beta by 1 plus beta and some value is there. That means denominator is increasing. This total value is decreased when compared to the fixed bias. Similarly, in the case of emitter feedback bias, if you observe this part, what will happen to the denominator? RB plus RG. Here it is RB plus RE. But here it is RC plus RB plus RE. That means if this total part is increasing, means what will happen to this part RC plus RE by RB plus RC plus RE? This is going to increase. That means total denominator is increasing. Total denominator is increasing when compared to this denominator. This denominator is increasing. That means the S factor is nearly equal to the stability factor is nearly equal to 1 in the case of collector to emitter feedback bias circuit. But it is not equal to 100. But it is nearly equal to 1. But it is not equal to 1. Okay, this is about your collector to emitter feedback bias.